So guys, we're almost done. This is the last exercise we're going to do. It's about friction loss, and in this time we're going to apply the mechanical energy equation. You recall from AFT number 1, we were always given the friction data, so HF as a number. But in this case we're going to calculate it, so let's do it. Let me explain you this little exercise. We have tank number 1 and tank number 2. We have A and B, so fluid is going to flow through here. There is an inlet, and then you have a pipe, you have a valve, you have this valve right here, and you have also another valve right here. They give us the specific gravity, they tell us it's crude oil, they give us the density, the viscosity, they tell you with respect of the ground, they gave us the height of tank A, and with respect of the ground also the height of tank B, which is negative. They tell us that we're using steel pipes, so we will have that roughness right here. The diameter is through all the pipe, the diameter of 3 inches, schedule number 40. I already took the precaution to calculate it on meters, it's right here. And the total length of the pipe is about 45 meters. So, and we have 2 valves, 2 gate valves, and we have 1 L valve right here. Perfect. The question will be, what is the volumetric flow rate? And for this you need to calculate velocity, but we don't have velocity, so we need to go and use our mechanical energy equation. So just recall that we're using letter A right here and letter B right here. This is being pushed by atmospheric pressure, so we cancel both pressures. Velocity in A and velocity in A is static. Velocity in B, we cannot cancel it because we're not doing the balance right here, I think. Okay. No pump, no workout, so actually we are left with this right here. So once again, why I didn't cancel B, because if you were to check, is before it leaves the pipe. So it's leaving the pipe, this will be B. And then it goes to the fluid right here, to the tank. So we got this right here. This was our mechanical energy equation. And I want to calculate the volumetric flow rate. So this is very interesting, guys. I'm looking the velocity. If I would make the balance on exactly here in the tank, it will be 0 and it wouldn't work. Why would I want to calculate the velocity? Because we need Q. Remember, Q equals the velocity in the pipe times the area. So that's why we are doing the balance right before it goes out. So we need velocity, which is right here. We have gravity, yes. We have heights, yes. We have friction, no, but we can calculate it. Actually, it's right here. We can calculate the wall friction and the friction, fittings, valves, and so on. Then recall this is for a wall, and this is for the inlet, and the gate valves and the eel valve. So we have 1 friction due to the valve of eel. We have 2 times the friction of the valves, gate valves, and we have 1 friction due to the inlet, which is right here. Don't forget, guys, this little fitting right here will cause a friction loss. So once again, we just need this and this. The K values I found in my databases are these, so we're set. Once again, we have this right here, which is K. Okay. Sorry, and then I have this, which is the wall friction, and this is the K values. So from this, I only have L divided by D. The length was 60 something. Wait for it. 45 meters, and the diameter is 0.078. So if I wanted to substitute here, I will get 576.9 times the factor friction here, and 1.49, and of course don't forget the velocity heads. Now let me substitute this value, which is HF. HF equals this value. And what's HF? Well, HF goes right here in equation number 1. And then we will have everything. This will be a number which we already could calculate. We will have HF in terms of velocity, and we have velocity to the square. So it will be very easy to substitute it. So once again, we have the changes on height. Guys, probably you've been following the course in YouTube. You probably seen that there are plenty of videos on the mechanical energy, velocity to friction, pumps, but eventually you go and check out in the playlist that you don't have the complete material, and that's because the complete material is actually in this website, Incompressible Flow course. So once you get here, you got all the theory lessons right here in this tab, course theory. Let's see, for example, the mechanic energy equation, and then you will be able to see how it's structured. For example, the overview of the block. You start with the theory of all these are sections. So for example, let's go and check out why mechanical energy equation is needed. You also got an introduction to this section. You got, for example, also this class 7 right here. You got a description of the class, written description. You got the video, high definition video, and you can also ask any question right here. So for example, what is that in minute 7, or whatever your answer is, or question actually. You got recommended problems here, all those problems in block AFD. And it's very important also, we got a content of 15 hours, so that's pretty awesome. If you want to check it, you should register for an account and you will get access to all this material. We have this velocity head, and this right here is the energy loss due to friction as a function of velocity of B, which we don't have. But thank God this equation has only one variable, which is B, velocity of B. So we have the gravity, we have 6 minus 9, so actually we have a delta of 15 meters. I add all these, so actually this will be one number here, this goes right here, and then the one for it goes here. So let me add this and this. You have 2.49, this value was 294, and this still is function of friction factor. So I have actually two variables. I have friction factor, which is dependent on the Reynolds number, which at the same time Reynolds number depends on velocity, and friction factor depends also on relative roughness. So we have a problem right there. I told you Reynolds number is function of velocity. The relative roughness, I could calculate it right now. So one thing I might do is, for example, calculate the Reynolds number in terms of velocity, and I got it right here. That's my Reynolds number. So I will have one problem, guys. As you can see, I have Reynolds number as a function of velocity, and I need Reynolds number in order to calculate this value, so I could calculate this velocity. So what I think, we could propose one velocity, calculate the Reynolds number with this equation, then find out what's the friction factor according to Moody's or chain equation, and then verify in the mechanical energy equation, which is right here, verify in number 4, this equation. Since I got friction, I could solve for this velocity. And the interesting part right here, guys, is that if I calculate the velocity in B of 4, and is the same as the velocity I recommended, which was in this case 4 meters per second, I'm done and I don't need to iterate. So if this velocity is not the same as the velocity in the verification, then you need to try another velocity. Okay, so that is more or less the strategy. Let's do it. So let's propose 4 meters per second. So 18,000 times 4 is something around 7.3 times 10 to the 3. Finding in the Moody's diagram, recall that we have factor friction in the Reynolds number and the relative roughness right here. So checking this, I found out the friction factor. I will go to this equation, guys. Recall substituting this equation. So I got 294 and I got this right here. And what I see is that I get, if I solve for this velocity given this friction factor, I got 353, which is not the same as this 294. So I gotta propose a little bit less velocity. Let me try 3.5. I calculate Reynolds number with the same formula right here, 6.5. I got this friction factor, which is a little bit less. I substitute it in this equation and solve for velocity, and I get 256. But I don't need 256, I need 294. So let me once again try something which must be a little bit more than this and a little bit less than 4. So I try 3.75. Reynolds number is almost the same. Friction factor is the same. Substituting this velocity 3.75 to second power and then the friction factor times 577 plus 25 or 2.5, and I get a velocity of 294.8, which is pretty near to that 294. So I will say this is a velocity which is, let's say, according to the friction. So let me once again go. What I did is I predict the velocity, calculate the friction factor with that velocity, and if the right side is the same as the left side, I'm done. And this was what I did. I tried 4 meters per second, I tried less, which is 3.5. Then I saw that I must be in between, so 3.75, it's a very good velocity. So don't forget that we are asked to calculate the volumetric flow rate. Volumetric flow rate is essentially velocity times area. Velocity, we just guess it by iteration, is 3.75 meters per second. The area is P divided by 4 times the diameter to the second power. I get this. Or the equivalent to Q equals 64 cubic meters per hour. So let me show you some tips. This friction is the equivalent to that of the wall. This friction is equivalent to that of the shape. Calculate them as we did here. Let me show you. This one was the one of the wall. Do it by separate. Then calculate the one on the shapes and fittings. And then you can, at the end, add them up. So for example, HF, you know, is the addition of both. Actually, I have it right here. You already got your value of HF. You got your value of HFS. And if you can't, I will definitely recommend to take out the velocity. So you have, I don't know, F, L, D plus the addition of K values. And this will be your friction. And once you got your friction, just solve for the variable, which is the mechanical energy equation right here, and you're set, you're done. So this one was a very interesting topic because it had the example in which we don't have the velocities. Not having the velocities is one of the worst case scenarios in the mechanical energy equation because everything depends on velocity. Reynolds number depends on velocity. What else depends on velocity? The velocity heads depend on, of course, velocity. The friction depends on the velocity. So we have many things that depend on velocity. So that's the worst case scenario. Q depends on velocity. So not having velocity will be a very, let's say, courageous or interesting problem to solve. I have way more problems like this. So just check out here, part number 1, incompressible flow, and go to the solve problems section. this was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, if you were analyzing or studying pumps, you have it here, the pump block, and then you have the sections. If you were, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. If you were studying positive displacement pumps in rotatory and reciprocal are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.